All right, welcome AP. It's a new chapter, a new day. We got chapter 16, acid-base equilibrium. So it's a continuation of chapter 15, equilibrium, just concentrating on acid and bases. This is a big chapter. We got like 10 sections in here. So not only does it connect to chapter 15, but even chapter 17, which is more acid-base equilibrium. So I like to call it the part two to what we're doing in here. So let's get started with 16.1 and 2. We have two very important definitions for acids and bases. One is after a scientist named Arrhenius, and the other one is Bronsted-Lowry. Some people call it Bronsted-Lowry. Both of them had two very distinct definitions of what makes an acid and a base a base. So most of the time in real life, acids, as we know it, taste very sour. Like lemons and limes and oranges. They also can cause dyes to change color. We know that by doing a lab with lemons, the invisible ink lab, where you take a lemon and you put it on paper, kind of like write a word with lemon on paper, and then you take a heat source underneath it without burning the paper, and then you actually see the color change. Bases are very bitter and feel soapy. Most of the bases we come into contact with are cleaning products. Milk is a little slightly basic, but that's about the only food or drink I could think of that we come into contact with bases. With acids, about pretty much everything we eat is some type of acid form because our stomach is acidic. So first definition is Arrhenius. Arrhenius said that an acid has to be a substance when you dissolve it in water, has to increase hydrogen, okay? So when you take like HCl and you dissolve it in water, remember chapter 14 or chapter 4, dissociation, HCl is a strong acid, so 100% dissociate. You can break it up into H plus ions and Cl minus ions. So I am increasing my H concentration because I produced hydrogen. For a base, he said when you dissolve it in water, like sodium hydroxide, which is a strong base, it will produce hydroxide. Okay, doesn't seem like too hard of a definition. So in one case, we need to make sure that our concentration for hydrogen is increasing, and as a base, our OH is increasing. Well, not every acid or base starts with the H plus or ends in hydroxide. You're going to notice that as we go out this chapter, there's going to be some other bases that we see that don't end in OH. Like the most famous base I'll even tell you is ammonia. It's a weak base. You're going to see us come more in a detail with him about 16.6. That's a very famous weak base. That's ammonia. But notice it doesn't have OH. So ammonia has another formula that we write. It's ammonium hydroxide. And that's where you see the OH when it dissociates. Okay? So if not everything that's an acid starts with an H or a base ends in OH, let's look at the other definition of Bronsted-Lowry. I just abbreviated BL. For an acid, he said it has to be one that donates a hydrogen. Okay, so if it donates a hydrogen, who's going to get it? Well, that must mean the base. The base is going to accept that H plus, aka a proton. So therefore, a Bronsted-Lowry base doesn't need to have OH in it. So like this NH3, I can accept a hydrogen from somebody because if I get a hydrogen, aka a proton, I know you've seen this guy before, ammonium. Still doesn't have OH, but that's okay. So like ammonia is considered a Bronsted-Lowry base because he can accept a proton. But it doesn't mean it's an Arrhenius base because I don't see OH ions. So be very careful with the two definitions. So our first learning objective is 4.8. Can you identify a Bronsted-Lowry acid base and its conjugate? Okay. So by definition, what is a Bronsted-Lowry acid or base? And then read the learning objectives. There is a topic called Lewis acid bases, not on the AP test, okay, which are not even in the notes, so don't even worry about it, okay? Take a minute to read, highlight, and come back to me so that way you know what does AP expect you to master. Why up here did I say proton? Accepts and donates a H plus, aka a proton. Well, let's go back. Why H plus is called a proton? Back in the day, on the periodic table, hydrogen, okay, big ol' H, has an atomic number of 1. And remember that atomic number is protons and electrons. And then you have that 1.00, well, our periodic table says 008, that's the mass number. And remember, mass is protons plus neutrons, okay? So if the mass number is 1, and we already know we have 1 proton, so that means the H atom has a proton, no neutrons, and 1 electrons. Well, what happens if we lose an electron? The only electron that he has, aka becomes a cation, then the atom then becomes this cation, H+. So then what's left over? All you have is a proton. It has no neutron, and the 1 electron that he had, it's missing. So that's why we call it a proton. So H+ is what we call a proton in a proton transfer reaction. And we're going to use this proton transfer reaction in Bronsted-Lowry. So this proton transfer reaction is taking that hydrogen from the acid, called an H donor, and we're going to give it to the base, H acceptor. The law of conservation says you didn't lose or gain, you just rearranged it. And that literally is the perfect example of the law of conservation, whereas the acid's going to donate it to the base, and the base is going to accept it. Okay, so these are called proton donor reactions, okay, which are still acid-base reactions too. So then once you have this acid or base, then you have what's called conjugate acid-base pairs. These are on the product side. So your Bronsted-Lowry acid-base, this acid and base, those are your reactants. But the question is, what do they turn into? They're called conjugates. Conjugates in chemistry mean the opposite, which means if you start with an acid, you're going to get a base. And if you start with a base, you're going to produce an acid. So whatever left of the reactant after the proton is donated, it's called a conjugate base. And whatever is left over of the base getting that proton is called a conjugate acid. Okay? So before we practice an actual reaction, let's make sure we actually understand this proton donor and accept. So if I call these acids, okay, so I'm calling these Bronsted-Lowry acids, and Bronsted-Lowry acids, they're going to donate not just an H, but an H+. So the question is, what are you left over? Well, if it helps you, think of it as Chapter 4 dissociation. So when Chapter 4, we took a substance, we'll call it XY, and we put it in water. We didn't have to put water into the equation, okay? We just got the X and we got the minus, okay? Well, I'm going to take this proton, and what am I going to be left over with? Well, all I'm going to have is F minus, because think of it like a balanced equation. I'm going to get H plus, and I'm going to get F minus, okay? So that's your conjugate base. It's the opposite of this acid version. As they said right here, whatever is left over, okay? When you dissociate, okay, this proton donor, aka the acid, you can only donate 1 H plus at a time. So even though this next example has 2 hydrogens, I can only take 1 hydrogen away. But what am I left with? Well, I'm still left with an H, and I'm still left with that sulfur. But now what about the charges? So remember, in the beginning, I had no charge. When I add these up, I need to make sure that it's neutral. So what's my conjugate base? HS. Okay? Do you have to write these equations to figure it out? No. I'm hoping that you don't have to eventually, so you can just write it down. So if I give up a proton, so I take that hydrogen, I now have NH3, but do I still have a charge? Well, remember, I took a hydrogen and the positive. So that positive now is gone. So I have what's called ammonia. I'm going to take a hydrogen, which means basically he's gone. I'm taking that proton. So then I have ClO4 minus. And I'm going to take a hydrogen, but not only a hydrogen, but I'm going to take the proton, H plus. So I take one of the hydrogens, but I also take that charge. So what am I left with? pH3. I'm going to take that proton, and I'm going to be left with CO3, but what happens? So H plus CO3, it's not negative, because remember, it's got to equal -1, and you already have a +1. So that must mean -2 and +1 have to equal -1. And we know this guy called carbonate. Well, what if I mess with water? Okay, so I take one of those hydrogens. Now, before you write this, okay, or actually, not the positive, because remember, we took a proton. So this plus and this has to equal 0 on the water. You know that is not correct. Okay, you know you do not write HO. So that is what we're left with. Okay, all right, let's try it the base way. So for an Bronsted-Lowry acid, they donate the proton. So a Bronsted-Lowry base accepts the proton. And when it accepts the proton, it becomes a conjugate acid. Remember the opposite version. So basically, it's like saying H plus is added to it. But be very careful, okay? We're not doing crisscross. We're not trying to make compounds. We're just putting them together, okay? So basically, these two come together, and you make your acid. And we know this guy. We've seen him before. This is acetic acid, okay? This +1 and -2 come together. So now I have two hydrogens. Well, I don't write hydrogen H and H. I just add up the hydrogens. And what's going to happen to that charge? Well, a 1 and a -2, that means I'm going to be left with -1. So then I have a negative. If I add a hydrogen on, where can I add it? You never mess with the middle. So when you accept, you can either add to the front or the back. In this case, I would add to the back because I already have hydrogen sitting right there. So I'm going to get my CH3 in H3, but remember I added a proton, and a proton has a charge. So now I'm going to have a plus. These two just get added together. Okay, so I'm going to get HSO4, 1 minus 2, there's going to be my -1. Okay, so same thing here, we're just accepting a proton. Okay, so this is not making a compound, ladies and gentlemen. This is showing how a proton is added to this substance. So I'm going to get H and -1, so just HCN. If I add a hydrogen to water, well, I'm going to just change this to 3 hydrogens and an oxygen, but I added a proton, and a proton has a charge. And this is not very familiar to us a lot, but it is going to be in this chapter. This is called hydronium, which I know the name's coming up. H plus and a negative, so I'm just going to add those two hydrogens together. And 1 minus 1 is 0. Now 1 minus 3, that's going to be -2. And I'm going to add this hydrogen to it. And I know this polyatomic looks a little familiar to you. Hydrogen phosphate. And that's Bronsted-Lowry acids and bases. So what happens when we take those Bronsted-Lowry acid base and we make a reaction? So this is what's called those proton transfer reactions. Okay? So the H, so I have water and I have ammonia. Okay? Water is going to donate a proton. And because it donates a proton, we call that a Bronsted-Lowry acid. So this is my acid. So as you see, one of the hydrogens and only one proton comes over to ammonia, and ammonia is going to accept it. So the water was the donor, the H in the water was the donor, and ammonia is going to accept it. So now I'm going to be left with OH minus. So because it was an acid, it now turns into a conjugate base. And ammonia accepted the hydrogen, so now I get ammonium, and that's a conjugate acid. So we do these little brackets to show the pairing. We call them acid-base pairs. And because this is at equilibrium, ladies and gentlemen, make sure you do your double arrow. So equilibrium, okay? So let's practice. I have HSO4 and CO3. I want you to identify who's the acid, the base, the conjugate acid, and the conjugate base, okay? Well, you have to think. CO3 can't be the acid, okay, because he doesn't even have a proton to donate, okay? He's got to be able to accept it because this HSO4 is the only one that has a proton. So this H is coming over, but remember, it's a proton. So if this is donating, then my donor is an acid. Okay? So that's my Bronsted-Lowry acid. And that means my CO3 is going to accept it, which means my base. Okay? And because this was an acid, notice what happened. It turned into SO4. So I'm just going to abbreviate it. This is going to be my conjugate base. And CO3 was a base, and it turned into hydrogen carbonate. So that'd be my conjugate acid. Okay? So you have to think, ladies and gentlemen, which one is capable of donating and accepting? What if they both have available hydrogens to donate or accept? Okay? So now you have to follow. You have to follow the hydrogen. So notice over here, this HPO4 became the H2. That means he accepted. He got a hydrogen, and who did he get it from? He got it from the water. Okay? So water donated, and HPO4 accepted it. So if this is my donor, that means this is my acid, and that's my base. And my base turned into a conjugate acid, and my water that was an acid turned in, to a conjugate base. Okay? I have NH4. And I have OH. Now it looks like NH4 turned into ammonia. So it looks like this guy donated that proton. And OH had one hydrogen and now has two. So this accepted it. Okay? So my donor, ammonium, is my acid. OH is a base. OH will always be a base. Okay? And turns into my conjugate base. And my OH base turned into water. Conjugate acid. Okay? Hopefully not too difficult, but this whole chapter we're going to be practicing. I want you to notice something about water, and I know I had it on here right there. Our water, in this case, was an acid, but can't water also be a base? Yes, and we have a name for that. When a substance can actually act as either an acid or base, we call it ampriprotic. It has properties of both an acid and a base. Who says it always wants to donate and who says it always wants to accept? It can do both, okay? So we're going to do an example of write an ampriprotic, okay? And I'm calling HSO3 ampriprotic, which means I want you to write a reaction when it reacts with water, and when it acts as an acid in one case, and when it acts as a base. And then identify the conjugate acid and base. So water loves to be an acid or a base, but every chemical can do it too. So if I said hydrogen sulfide is ampriprotic, so I'm going to say HSO3 minus, and remember every ion is aqueous, and I want to react it with water. Now people, water is a liquid. Don't be putting aqueous on my water. Equilibrium. Now we're going to do the same thing here. The only difference is it's that hydrogen sulfide. In one case, we're going to call it an acid. In the other case, we're going to call it a base. So if this is an acid, we know it's going to donate that proton, and that proton's coming over. And I like to write the H and the plus because I like to remind myself the plus is coming with it too. So if hydrogen sulfide is the acid, that means water is going to be the base. Now this acid is going to turn into SO3, but remember it took some of the positive, which means this SO3 got more negative. So it's going to become -2. And it's an ion no matter what charge. The water accepted the proton, so now it's going to become H3O. Remember, it donated a proton. It donated with that charge. And that's also going to be aqueous. So my HSO3 turned into a conjugate base, and my water turned to a conjugate acid. Now there's a law in chemistry called, you know it, law of conservation. But did you know the law of conservation doesn't just mean of mass and matter? There's also charges. The law of conservation of charges. They have to be equal on both sides. And check this out. -1, nothing's on water. So that means this side of the equation is -1. Equals about this side. -2 and +1, -1. You have to make the charges equal each other because the law of conservation said that. Just because somebody donated and accepted a proton doesn't mean you created anything new, you rearranged. So let's do the same thing in this case for a base, but now I'm going to call my water the acid. So now one of the hydrogens, and only one proton is coming over to this base, and he's going to accept it. So I'm going to have H2SO3, and notice this plus and minus, they're going to cancel out. And this is going to turn into a base, turned into a conjugate acid. Okay. My water donated, so what am I going to be left with? Well, I'm going to be left with only just one oxygen and one hydrogen. But remember, it took some of the positive, which means I'm left with negative. And then OH. And if you check your charges, I have a negative, nothing, so -1, equals, this side has nothing, and then hydroxide is -1. So you just need to make sure they equal both sides. Okay? So my water was an acid, and it turned into a conjugate base. Okay? I want you to make a note of this. Anytime you see OH, it will always be a base. And anytime you see hydronium, it will always be an acid. Okay? Always, always. The problem is with water, it can act as an acid or a base. And what do we call that? We call that ampriprotic. Okay? So our next learning objective is about the strength of the acid and the base. Is there a difference in every acid and base and their strength based on the structure? So take a minute. This is learning objective 9.F, and there are 5 objectives that AP expects you to master. So take a minute, read, annotate, make some notes, and come back to me. The strength of the acid. If you have an acid that's very strong, when you turn it into its conjugate, it's going to be very weak. Like, for example, that HCl. That's a strong acid. But when it loses that proton, it's going to become Cl-, which is a conjugate base. Because this acid is very, very strong, we have a name for the counterpart, for the opposite. Okay? We call it negligible. Okay? And I'm going to get to what that means in just a second, but let's look at the 3 right here. We can categorize acids and bases into completely dissociates. Hey, that sounds familiar from chapter 4. Strong acids completely dissociate, so do ionic compounds, and strong bases completely dissociate, like HCl completely dissociates into H+ and Cl-. Okay? Because this is a strong acid, this Cl- it produces, that's going to be my conjugate base. But it's so beyond weak, it doesn't even have a measuring system for it. So we call that negligible. Okay? Negligible just means it's so weak, okay? And I know I have it right here. So substances that are negligible, they are beyond weak, that you can't measure their strength anymore, okay? What if you start with a weak acid? Okay, which remember, weak acids partially dissociate into aqueous substances. In chapter 4, we had two categories, weak acids and weak bases. Well, we're not going to memorize every weak acid and base because you're going to know which ones are the weak acids and bases as we go through this chapter. The reason why they partially dissociate, because you got to remember, in that solution, you have a mixture of molecules and ions. So remember in chapter 4, when we drew those particle diagrams, we had the plus, we had the minus, but we still had the ginormous acid that was still sitting in there, okay? So these conjugate bases, they're still going to be weak. So the acids turn into a base, and that base is going to be a weak base. So whatever that weak acid is, it's going to turn into a conjugate base, but the base is still going to be classified as weak. So if you notice on this table right here, acetic acid is HC2H3O2, one of the most famous weak acids out there. He's actually right here too. The reason why AP writes it in the structure is to help with drawing. So I'm going to write both versions. We will get to the drawing chapters too, but they're both the same thing. If you count it up, they both have 4 hydrogens, 2 oxygens, 2 carbons. So if it's a weak acid, over here, when it donates that positive, that proton, you're still going to get a weak base, okay? And if substances are so beyond weak, we can't even measure them, we call them negligible. So if you notice this table, okay, as you go up on the left side, these are the stronger acids, okay? Right here, there are 7 strong acids, but they only listed 3 of them. Not a problem. But remember I told you anytime you see H3O+, okay, its conjugate version is water. It's so negligible on this side that we can't even measure. So the stronger the acid, the weaker the base, okay? And it says it right up here too. The stronger the acid, the weaker its conjugate base. On the flip side, what if you go to negligible acids? They are so beyond weak that what they're going to happen is so weak, they'll turn into strong bases, okay? So always think of it as strong acid will turn into a negligible base, and a negligible acid will turn into a strong base, okay? Seems like pretty simple. A weak acid, weak base. Or weak base will turn into a weak acid, okay? You won't know the strengths of them until we actually do some calculations, some plugging and chugging, okay? So this chart is just to help you. As the strength of the acid increases, the more weaker the base becomes. So the stronger the acid, the weaker the base, okay? And vice versa, okay? All right, AP, get ready for those calculators. I'll see you on the next one.